Hello. I wanted to try and produce a better video than my previous one. I had very limited resources here, so I'm now trying a direct upload instead of the previous version. Anyway, the reason for this is to talk to you about the carbon problem and how to resolve the carbon in the atmosphere. I believe it is achievable, requires a certain amount of money and obviously commitment, which we haven't seen from our political masters really in any way, shape or form. But if we can reduce it to money and the technology is broadly available, then maybe there are some benefits which they can have a look at. So what's the principle? The principle is to take the carbon in the atmosphere, to remove the carbon from the atmosphere, bring it out as a solid, and then that carbon can be distributed through the world, can also be used as fuel. But primarily, certainly for the first few years, we would want to probably bury it and put it back into the earth where it came from, whilst the other technologies are developing around it. And hopefully, after some time of removal of all the carbon from the atmosphere, we'll actually be able to use it as a renewable resource. So how does it work? Well, primarily what we need to do is to disassociate the carbon molecules from CO2 in the atmosphere. I've done a few sums on this, which I will share with you, and it might get a bit complicated, but trust me, it's worth it. Okay, according to my calculations, we're producing something in the order of 6 times 10 to the 12th kilograms of carbon dioxide per year as a planet. In order to disassociate the carbon from the CO2, it requires energy. And the amount of energy required is 393.5 kilojoules per mole to disassociate those two parts. Each kilojoule requires 3.6 watt hours to produce it, which relates to 1116.6 watt hours per mole to disassociate, and we have 12 grams of carbon per mole. Which bottom line there is 118.05 watt hours per gram of carbon, or 118.05 kilowatt hours per kilogram of carbon. We need to offset 7.083 times 10 to the 14 kilowatt hours. We need to use the energy requirement to offset the current usage of carbon is 7.083 times 10 to the power 14 kilowatt hours per year. The equivalent daily rate there is 1.94 times 10 to the 12 kilowatt hours. If we would use solar power to provide the energy, somewhere around the equator region, we've got about 200 watts per square metre of usable energy. Assuming the sun shines 12 hours a day, that gives us 2.4 kilowatt hours per square metre per day of energy. If we're going to be using up square meters using solar power, and obviously there are many ways of doing that, but we're going to need, based on 200 watts per square meter, 8 times 10 to the power of 11 square meters of equatorial land. That's approximately 17% of the area of Australia. We could also look at that as 808,561 square kilometers. A total land requirement. Now obviously we're not going to take over that much land because it's not going to be very usable, so what we need to do is we need to break down the producers of carbon, these what I like to call carbon factories, into relatively small modules, and each one of those, assuming that we have 100,000 of those altogether, which 100,000, that's quite a lot, we could then break that down to the amount of land that we require per plant of only 8 square kilometres per plant. So 8 square kilometres and 100,000 plants required, spread somewhere around the equator. We don't have to put them all in Australia, obviously. So how much energy are they going to need to produce? Well, according to my calculations, and obviously these are subject to verification, each plant needs to produce 19,405 megawatt hours per day, which means that each plant has to have a capacity of 1,617 megawatts. Okay, the hour calculation comes in obviously because we're multiplying that by 12. And what's the output from the system going to be? Well, the output will be 60,000 metric tons of CO2 per plant per year. Or that will be processed, sorry, that's the carbon that comes out. The carbon that comes out is 16,363 metric tons of carbon per plant per year, 44 metric tons of carbon per plant per day. Okay, so 100,000 plants, 44 tons of carbon per plant per day. And we need to find a way of obviously removing that and taking it somewhere else. The cost, I reckon, is about £16 million per, that's UK pounds, per plant, which is essentially a one-off cost plus some maintenance, and of course there's all the transport costs associated, but at least the fuel should be free. The cost, if we assume the cost of, that's based on a cost of 1 penny, that's 1 UK penny, which is 1/100 of a pound, per watt. Okay, so we're looking at 100,000 plants, £16 million per plant. I'm going to have to stop there. I'll come back with another video later.